Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games, and welcome back to 3D Games and GameMaker Studio 2. So the last video I made was a quick little fix about the 3D camera look in 3D with regards to the camera's pitch, and well, first person and third person. It would apply to third person cameras too. And now I'm back to talking about shaders. So I was initially going to make a video on spotlights next, the third type of lighting. I've already done videos on directional and point lights, and I was going to do spotlights next. And then I made a demo for spotlights using the Vertex shader, and it looked kind of bad. And I wanted to talk about lighting in the Fragment shader anyway at some point, so I'm just going to do that first. Spotlights will come next. So, if I were to go to the... where is the shader? The 3D Basic Stuff shader, or whatever I've called it. I'm going to split this into two columns, one for the Vertex shader, one for the Fragment shader, and I'm going to increase the font size again so that you can actually see it. At the current moment, lighting is calculated in the Vertex shader, and fog is calculated in the Fragment shader. And that's fine for things like directional lights and point lights, or at least it's mostly fine for point lights. If you look closely, you can see a little bit of weirdness with point lights done in the Vertex shader. If you look closely at the light on the ground here, you can see it's sort of a hexagon because these squares are composed of two triangles each, and each vertex gets lit independently of the others. If I were to go and disable the texture in that the floor is drawn with, whoops, something like, I'm just going to comment that out so I can come back to it later. Set the texture to -1. Then you will start to notice much more the lighting and the way it sort of cuts the squares in half. You can get around that with the Fragment shader. I'll leave that as it is for now so you can see the difference at the end of the video. So, also as a side note, smooth shading, you've probably seen smooth shading at some point. I mentioned it when I started talking about lighting shaders in 3D a little while ago. If you've been wondering how to accomplish that, that is also an effect of putting the lighting code in the Fragment shader, which I will also show off at the end of the video. So right now I have a directional light, which is commented out, and I have a point light. I'm just going to, I think, copy this all over to the Fragment shader first. The fog calculation can stay there. You can have it enabled or disabled if you want. I said copy, but it really should be cut and paste instead of copy and paste. There is also the matter of the vertex color varying, which is normally just in color in a pass-through Vertex shader, but I have added some additional code to make the lighting work. I'm going to move that additional code to the Fragment shader also. I'll turn this into a valid line of code later. Let's see, the uniforms can also go over here to the Fragment shader. Where are the uniforms? I'll just put them over the fog uniforms. Okay, so we're mostly cleaned up. As it turns out, moving lighting code to the Fragment shader isn't all that complicated. It's pretty much the same thing as the Vertex shader, except you do different things with the colors at the end. All the calculations are the same. There's a couple of variants I'm going to need, and for the sake of not making things unnecessarily complicated, v_world position is something that was there for the fog calculations. I am going to rename that to v_world view projection position, because it is, instead of just the vertex's position in the world, it is the vertex's position after it has been transformed by both of the camera's matrices. So giving it the name world position would be a little misleading. I'm going to replace those variables. This code is commented out anyway, so it's not really important, but if you're going to include fog in your code, which I am not for the sake of not overcomplicating the tutorial, you may want to give it a better name. So over here, if we come back to the Fragment shader, we're going to need a few things. Specifically, world position and world normal. These do not exist in the Fragment shader. Or I should say, specifically the attributes in position and in normal do not exist in the Fragment shader. Each fragment that's drawn has no idea where it is in the world. It has no idea how it's oriented, what its normal is oriented. The only things it knows is whatever you give it via varyings. So we should be used to doing this by now. Let's make world position and world normal both a varying variable. Have I commented on how that sounds kind of redundant before? Varying variable, because that's kind of what variables do. That's why they're named variable. They vary in their value. All right, whatever. So there's going to be vec3s. I'm going to actually call these world position and world normal. I realize names are probably complicating things because world position was what the fog varying used to be called before I renamed it a minute ago. If you've been following these videos, you probably remember that the value of a varying is going to be interpolated over a triangle when it's passed from the vertex shader to the fragment shader. So we are going to take the same 3D calculations that we used to get to the world position and the world normal in the vertex shader lighting, and we're going to, instead of saving them to regular variables, we are going to assign them to the varyings. So world position, world normal, that's the same calculation as before. The position is the world position times a vector 4 made of the input position and 1, and the world normal is the world matrix multiplied by a vector 4 composed of the input normal and 0. Also, if you want, I don't think I mentioned this in the fog video, but since the worldview projection calculation is the same as the GL position, you can just use GL position as a regular variable and grab the XYZ there. I will leave a comment. To me, there's no point in calculating the same thing twice. To some other people, I don't know, using GL underscore position as a regular variable may not sit well with you, so I'll just leave that in a comment. So let's come back to the fragment shader. How about to make this cleaner, I'm actually just going to delete the directional light code. I'll also delete the fog code. If I want to bring that back in a future video, I can just bring it back. There's no need for it to sit here cluttering up a tutorial code. And let's also actually just completely delete the varyings related to fog and the uniforms relating to fog. Okay, that's it, right? So we can start doing lighting code again. If we comment this invalid line so that it compiles, this will run and this will be unlit, and it will not actually run because world position and world normal are varyings that should be in the fragment shader, that should be declared in the fragment shader, and I need to actually replace the variable names. All right, false start. Let's try that again. So now it'll run, and it should be pretty much unlit. It's not pretty much unlit, it's exactly unlit. And we've kind of got a fresh start here, except not really, since we've already written the code that does the math. So it's not like we have to completely redo this entire thing. Okay, so if you remember how this works, you take the direction between the light source and each vertex, except instead of the vertex position now, it is the position of the individual fragment. The math is exactly the same. You take the length of the distance, which factors into the attenuation, and the attenuation just makes the light dim in intensity the farther away from the light source you are. Normalize the direction so it's got a magnitude of 1, otherwise the dot product will be a little bit weird. Use the dot product between the normal of each vertex, or in our case, each fragment, which is passed in via a varying. And this also affects the amount of light that each fragment receives. So if a light is hitting a fragment head-on, it's going to be fully lit. If it hits each fragment at an angle, it's going to be only partially lit. And then you put all those factors together, you put the attenuation, the dot product. By the way, and I forgot to mention this in actual earlier videos, and I feel kind of dumb because this is something that you'll probably see a lot. If you look up lighting code on Google, on Stack Overflow, on your code resource of choice, you will often see this value called n.l instead of light angle difference, and I'm going to make an effort to call that value that now. It's not like light angle difference is incorrect or anything, that's literally what it is, but since n.l is kind of sort of the standard that the world of shader programming has adopted in a lot of situations, I want it to be consistent with that so that if you look it up in the future and you see that, you're not like confused unnecessarily. It's just the dot product of the normal and the direction, the light's direction, hence n.l. I think I might have put that in one of the video descriptions or something a while ago. Anyway, you multiply all those factors together, the attenuation, the dot product, the light's color. You add in the ambient color so that unlit parts of the world aren't completely black, but instead they have a dull gray or something for the ambient color. You take the minimum of that value and 1. If you want to be careful, you could clamp it between 0 and 1 so that nothing is brighter than 100%, since that wouldn't really make any sense. That would start to make certain things look a little bit washed out. You apply the original color, which instead of in color should be v_v color, the varying, since we are no longer in the vertex shader. You don't want light to apply to the alpha channel, otherwise things start to look weirdly transparent. I think I showed that off in one of the earlier videos too. And then when this was in the vertex shader, the result of this was multiplied by the input color attribute. Here we want to do the same thing, except instead of the input color attribute, it is the v_v color varying variable. Yeah. Programmers aren't good at naming things. And since we are now in the fragment shader, and we also want to take in the pixel that is on the texture that we're looking at into account, we would multiply that by texture 2D, GM base texture, with the coordinates that are passed in from the vertex shader via the text coord varying. And in my case, this is stored in the variable starting color. And considering that, let's just do that. Starting color contains the color of the fragment if none of this was lit. So again, if I just commented this entire section out so that lighting was not actually applied, that would be unlit. Starting color would just be the base color. And if I leave that in, everything is going to be lit. Also, I suppose since the texture 2D pixel may have an alpha value as well, instead of grabbing the alpha from the varying color, let's just grab it from the result of starting color. Okay. So now I should run the game, and lighting works, and you can see the circle is much more round. That is an immediate bonus of calculating lighting in the fragment shader. You no longer have noticeable vertices anywhere where you try to calculate lighting, because each pixel is calculated independently, as opposed to just the vertices. And like I said earlier, this also allows you to do smooth lighting, which I will demonstrate now. So I'm going to make a sphere. I'm going to just make it, let's make it 16 by 16, 16, 16, 16, 16, 16. 12 steps is all right. Let's make it actually 20 steps. I want to say, generally, if you generate a sphere in like something like Blender, it'll be the precision will be something more like 20.
Hey.
Let us convert that to triangles. You can see it is very faceted now. This is called flat shading, also known as faceted shading. If I turn the lighting back on and turn those annoying dots off. If I were to, let's just sphere.3D, save that. I'm going to open up the previous one of these projects and load it in there first so that you can see what it looks like. Give me a moment. Okay, so I've opened up the previous project with the lighting done in the vertex shader. I've loaded the sphere into the included files. I load the sphere into the game in the Kamex create event, vb_sphere. I commented out the other things that are being drawn, and now I'm just drawing the sphere at 200, 200 in the room. It's also going to be scaled up 2 times so that you can see it a little bit better. 200, 200 isn't especially special, except that it's slightly offset from the position of the point light, which is at 250, 250, and somewhere in the air. So that should allow you to see all of the facets on the sphere. Okay, it looks like kind of a weird sort of disco ball, which may or may not be what you're going for. Generally, if you want to draw a ball in 3D games, you want it to be drawn smooth. In old GameMaker, in GameMaker Studio 1 and 8.1 and previous versions, there was a useful function called D3D set shading, That function is now gone, otherwise I would have probably mentioned it by now. It has been removed in GameMaker Studio 2, and if you want that effect, you need to now write the shader yourself, which is what we did in this video. So going back to smooth shading, Model Creator for GameMaker and pretty much every other 3D modeling program ever has a setting for smooth shading. So if I were to say the normal threshold is something more like 45, this is the angle where triangles that are adjacent to each other less than that angle will be smoothed. So you can see each of the quadrilaterals, or really triangles that compose the sphere, are at a very low angle compared to all other neighbors. So if we set the normal smoothing angle to 45 degrees, save the model, it's going to calculate its surface normals. It won't preview in the editor here, but if you go to preview model down here, you can see the triangles have now been smoothed. Not perfectly. You can still see some sort of ridges in there, but it's a lot smoother than it used to be. You can use this sort of trick to make something look like it's a lot more. You can use this trick to make something look like it has a much higher polygon count than it actually does. Anyway, let's drop in the new sphere model into this thing's included files. For whatever reason, I remember smooth shading in the Vertex shader looking much less. I remember it looking much worse than this. I guess it doesn't. Anyway, since we've done this in the Fragment shader, we can also drag the sphere into the included files in here. I'm going to do very much the same thing as I did in that other project. I am going to load it in. I'm going to comment out all of the other shapes that are being drawn. The collision data is still there, so if I run around, you'll probably see me running into invisible walls. But the thing that I care about is the what's being drawn. And now when I look over here at the sphere, it looks much smoother than before. You can sort of still see ridges in it if you look really closely, but it's much less noticeable. It's much less noticeable than it was before. For the most part, since lighting is being calculated for each pixel, which has a much higher degree of precision, it looks like an actual smooth round surface more so than something like a soccer ball or a D20 or something like that. Is there anything else I wanted to talk about with regards to smooth shading? I'm pretty sure that was about it. Let's bring back the rest of the world. I guess since I'm... Let's see, that is the player. Here is the ground. I guess since I'm done with showing off the precision of the lighting, I can bring back the ground texture also. And that is the player. Okay. I did not mean to turn the player back on. In the next video for spotlights, I will be going with the third-person camera because spotlights look more impressive when they're when you can see something moving in and out of them. But that is a topic for next week. All right, Fragment shader lighting. It is worth noting the Fragment shader is generally more expensive to process than the Vertex shader, not because this code is inherently slower, but because there are more fragments to process than vertices. Each of the shapes that I'm drawing only have a couple dozen, maybe 100 vertices in them. Modern graphics cards are fast. That is not something you really need to worry about. If you're looking to optimize your game because it's running slow for some reason, the Fragment shader is probably not to blame unless you're doing something really insane inside it. Doing a couple simple lighting calculations is not going to slow the game down significantly. Modern graphics cards are optimized to do exactly this as fast as possible. It's much more likely that your game is slowing down because... for example, you're trying to draw too many things, or more likely, instead of trying to draw too many things, you're being suboptimal with your vertex batching or your texture batching or something like that.
Hey.
Optimization in 3D is something I deal with fairly often, as you can imagine, and probably in the future I'll make a video on that too. Okay. That's the one disclaimer that I really feel the need to say about this, because I know someone's going to ask. Also, I realized I didn't actually talk about the math that goes into creating smooth vertices like this. Like I said, 3D modeling programs will generally do this for you, But if you want to do it yourself, perhaps you're trying to generate a model on the fly for something, that may be a calculation you want to do yourself. It's not that complicated. To make a long story short, you take the average of all of the normals of the triangles that are adjacent to a vertex. So, for example, if you were going to look at this vertex here, you would take the surface normal of this triangle. Okay, that's hard to see. It's easier in schematic mode. You would take the surface normal of that triangle, this triangle, that one, that one, that one, and that one, and average them together. And that would give you the smooth normal of each vertex. Again, math, I'll talk about that later. Anyway, I think that's it. That's all I wanted to do with Fragment shader lighting. In the next video, spotlights. And from there, I'll move on to some other shader things and some game dev things in general. I have a Patreon for these videos, so if you want to contribute to them being made, there's a link to that in all the usual places. Otherwise, the code is on GitHub. The code for this project is on GitHub. I hope you all found that useful, and I will see you all later. Special thanks to Edward Holt, Indie Punch, and Zenith for supporting these videos. If you want your name in the credits and to force me to pronounce them out loud at the end of every video, head over to the Patreon page in the video description and join the fun.